Okay, for what we have in this problem, it says here that during the period from 1790 to 1930, the U.S. population, P of T, or T we have in years, grew from 3.9 million to 123.2 million. Throughout this period, P of T remained close to the solution of the initial value problem, which we have in this particular formula. And okay, so we have P naught in reference to 1790. Okay, so you had a 3.9 million. And what 1930 population does this logistic equation predict? Okay, so again, so we have in 1790, okay, we have 3.9 million. And now looking at what we have, again, just kind of going back to our algorithms that we have with partial fraction decomposition leading up to natural logarithmic antiderivatives. Okay, you have this particular breakdown, and you're going to have this bit of a situation to arise with this formula. Okay, and going ahead to the formula, so you have dp over dt is equal to this item, and if I frame things where I can get it along the lines of this particular algorithm where I have p as opposed to x, what I can do is factor out, okay, the coefficient of the p squared term, and just factor out that times p, and you have that term minus, okay, you have 210.54. That's an approximation of this very small decimal number into 0.03135. Okay, and if I look at separating the variables, okay, so we have dp all over p times the quantity p minus 210.54 and we say we have is equal to negative 0.0001489 dt. Okay, so we have some very small decimal numbers in the mix. Now we have upon separating, again, so we have in line, okay, so you have this form of the equation. So we're looking at 1 over p times the natural logarithm. What is going to be p minus 210.54 at the top and p on the bottom. Okay, so we have, again, so you have 1 over 210.54 again, we have the natural logarithm p minus 210.54 all over p is equal to this very small decimal number times t, okay, followed by the constant, and multiplying by 210.54. Okay, so we have the natural logarithm of the absolute value p minus 210.54 all over p, and that's going to be equal to the negative, and going back to, okay, just the opposite sign of our leading coefficient in the presentation of this man's formula, so you have minus 0.03135. This time we have times t, and with 210.54 times the constant, we'll say we have plus alpha, and treating both sides as powers to which we're going to have e to be raised. And if I were to work on through, so you have e to the minus 0.03135t, and we have times e to the alpha, and e to the alpha, okay, we have it beta A constant raised to a constant is yet another constant. And so this comes down to, again, so now that we have the natural logarithm out of the way, we say that, and disregarding the pluses and the minuses, because that's going to be absorbed into the constant. Now, going back to 1790, again, the population was at 3.9 million. And if I plug into P, okay, so you have 3.9 minus 210.54 over 3.9. And e to the 0 is 1. We have beta times 1 is beta. Okay, and we'll say that for beta. Okay, we have to about the nearest two decimal places. Okay, this would be at minus 52.98. So plugging in this value for beta. So you have this formula to arise. Now, for the year 1930, okay, so we're now looking at P of 140. So we were looking at solving for P whenever T is at 140. There was quite a bit of number crunching involved. Okay, so we have this ratio is equal to, and we'll say to the nearest three decimal places at about negative 0.658. And if I multiply both sides of the equation by P, so I have this set up, and I got this P term by itself on the right. And if I take P away, so we have negative 210.54 is equal to right at negative 1.658 P. And with P as the population for the year 1930 that was projected, so that was about 127 million. Now, so you have right at 127 million for part A. And what limiting population does it predict? And when we had factored out, again, so you're looking at right at 210.54 million. And has this logistic equation continued since 1930 to accurately model the U.S. population? Well, since we have the population exceeded 210.54, so the answer to that is no.